I was flying through my slides. Okay. Oh, good morning, everyone. Welcome to my talk, Making Nuclear Fusion Possible, Enhancement of Structural Materials. My name is Simon, and I'm an undergraduate student, UC Lead Scholar from UC Irvine. This summer, I'm working with Dr. Nicholas Cunningham, all the way to in the back right there. I'll thank him later in my slides. And my faculty advisor is Professor Bob Burdett from the Materials Department. Now, before I move on and tell you how I'm making nuclear fusion energy possible, I want to tell you why. Why do we care about nuclear fusion energy? Well, in my opinion, there are many great benefits to nuclear fusion, but I've highlighted 3 points that I think are most relevant to our generation. Number one, nuclear reactors, fusion reactors, they do not produce CO2 emission or greenhouse gas, so it's pretty friendly to our environment. Number two, nuclear fusion reactors don't have a long-term radioactive waste storage, meaning we can cut down all the costs for waste treatment. And number three, fuel is abundant on Earth. Deuterium, an isotope of hydrogen, can be vastly found in any ocean water, or even here in Goleta Beach. Tritium can be actually self-breed inside the nuclear fusion reactor by interacting lithium with neutron. And as the diagram summarizes, when we interact deuterium and tritium, we get byproducts of helium and a high-energy neutron. Now, nuclear fusion reactors have a higher heat flux, meaning that we're now faced with a material challenge for our reactors. Now we would need a structural material that could withstand higher heat flux, higher doses of radiation damage, and higher doses of helium production. Now, recent studies have shown that nanostructured ferritic alloys, known as NFAs, are able to mitigate these damages. And what NFAs are basically strengthened iron alloys that are made up of what is called nanofeatures, NFs for short. And these NFs are made of yttrium, titanium, and oxygen. These nanofeatures are about 1 to 4 nanometers in size. They impede dislocation in the material to strengthen the material. They trap helium and prevent them from going to the grain boundary and forming voids, which can embrittle our material. And lastly, these nanofeatures can serve as a healing mechanism from damages due to the neutron. And visually, under a TEM, we can see that this rectangle here is our nanofeature, and it's 1.8 nanometers by 1.8 nanometers by 3.8 nanometers. And they're made of yttrium, titanium, and oxygen. Now, yttrium, one of the main components of our nanofeatures, are not soluble in iron, which is our matrix. So we have to use a process called mechanical alloying to physically force the yttrium into the iron. And this is done by mixing yttrium and iron powder with steel balls and mixing it in either a roller or a mill to process it. Now, if I want to make 3 to 4 tons of this material to build a nuclear fusion reactor, it's going to be quite expensive and difficult to do. So we want to eliminate mechanical alloying. And to do so, our group hypothesized that we can replace actually yttrium with scandium, another group 3 elements in the periodic table. And we can do so because they're chemically similar. Scandium is much more soluble in iron than yttrium. And because of this, we can eliminate mechanical alloying and proceed with traditional melt processing techniques. Now, one of the drawbacks of scandium is that it's currently more expensive than yttrium. And in terms of composition, I have converted the atomic weight of yttrium and scandium and converted them to weight percent. So as I've shown here, here are the composition of the 2 NFAs. And on the periodic table, scandium sits nicely on top of yttrium, making a very nice candidate to explore. So the goal of my project this summer is to reproduce these NFAs using scandium. I would examine if scandium, titanium, oxygen nanofeatures actually exist. And finally, I would compare the hardness of my scandium NFAs with the yttrium NFAs. And to mimic the processing technique of these yttrium NFAs, I've also mechanical alloyed my scandium NFAs, or scandium powder with the iron powder. Then I've heat treated using 2 different techniques. 850 degrees Celsius and 1,000 degrees Celsius for 3 hours in a furnace. And I've taken some of the powder and actually consolidated it at 1,100 degrees Celsius for 5 minutes. Now with the resultant powder and alloy, I've taken hardness on it, which could give me a suggestion of yield strength. And like I mentioned before in my the NFA slide, if I do have nano features in my material, which would cause dislocation and which would impede dislocation, I would have a high yield strength. So by judging from the hardness, I can kind of get a guess of if I had produced nano features or not. And after, I would look at it under an atom probe, which would give me an atomic scale in 3D of my material. And in this hardness chart graph, I've graphed the hardness value in terms of Vickers hardness versus the maximum processing temperature. Now, a couple of things to note here is that at 850 degrees Celsius and around 1100 degrees Celsius, my scandium NFA and my yttrium NFAs are actually fairly comparable. And one thing to notice here, another thing to notice here, is at 1000 degrees Celsius, my scandium NFAs actually has a much lower hardness than my yttrium NFAs. And my group came up with a couple of hypotheses about that, which I would be glad to explain in the question session. And here on your right is an image from Atom Probe. Each dot here actually represents an atom, and each color represents an element. So if you can see with the arrows pointing to these clusters, there are purple, blue, and green, which corresponds to scandium, titanium, and oxygen. This tells us we have formed nano features that are in our material. And these nano features are about 2.46 nanometers in size, in diameter, which is very small and ideal and comparable with our yttrium NFAs. The number density is 5.1 times 10 to the 23rd inverse cubic meter, which is also very comparable with our previous NFA. And the composition of the nano features are really comparable as well. So to summarize my talk today, nuclear fusion is a potential alternative energy source. It is green and it is safe. Nuclear fusion reactors require structural materials that are able to mitigate damages due to neutron and helium. Now my group has successfully produced not one but 2 NFAs that could potentially be used in nuclear fusion reactors. And in my hardness data, I found that my scandium NFAs heat treated at 800 degrees Celsius and my alloy at 1100 degrees Celsius are actually very comparable with our previous NFAs. And one important thing that I would like to note is processing time and temperature are actually very crucial to these nano feature formation. So in the future work, I would thermally age my samples, the powder, and would investigate in other traditional melt processing techniques to produce the NFAs. Then I would do mechanical testing on them. And finally, I would send, or we would send our powder to a national lab and have radiation tests done on them. With that, I would like to thank my faculty advisor, Professor Bob Baudet, for his continued support. Dr. Nicholas Cunningham, can I point you out? He's over there. Without him, I don't think any of this would be possible. He's very patient with me, and I'm really thankful for that. TV, my second mentor, sitting right there near to him. He has not only shown me the academic side of Santa Barbara, but also the social side. I'm also very thankful for that. And then the ODEC group, which is sitting in the corner right here. Thank you guys for coming. Of whom Kevin was actually a really big help for my presentation. I'd like to thank Erica for getting me here to UCSB. It's been a very pleasant experience. A couple of times I found myself in therapeutic sessions in the office. Because I was freaking out, I wasn't going to get into grad school, but I will, and I Yeah. Thank Maria and Kevin for their support. And finally, UC Leeds for their support this summer. And Zodon, this is Peter the Anteater, also my mascot for UC Irvine. So, thank you guys for listening.